Hello, this is Jatin Parekh, and I'm responsible for the product management of the Wi-Fi portfolio of Arista. Today, I would like to talk about CloudVision Wi-Fi's distributed control plane and how it makes Wi-Fi deployments resilient and scalable. Assume you have a deployment like this. The first thing that each AP does when it is deployed is to create a neighbor table. In this example, AP2 and AP4 are neighbors of AP1. Similarly, AP1, 6, 7, 5, and 2 are neighbors of AP4, and AP5, 7, and 10 are neighbors of AP8, and so on. So if you look at each of these APs, they create their own neighbor table. So now each AP knows which AP is its neighbor. And to be able to do this, each of Arista's AP transmits in its beacons a bunch of information that allows APs to realize which its neighbors are, which APs are on the same network as they are on. And also they share information about client count, channel utilization, both Wi-Fi and non-Wi-Fi, so that better R&M decisions can be taken. Now let's see how information about clients or stations that connect to these APs is propagated over this distributed control plane. So assume a client associates with AP8. What AP8 does is that it will share the state information of this client with its neighbors, which is AP5, 7, and 10. And this information has things like the PMK and the 11-hour key, the association state, if any login timeout or bandwidth parameters that need to be enforced, what IGMP groups this client has joined, etc. So that when it moves to the next AP, the new AP has the information of this client beforehand. So when this client moves to AP7, AP7 now shares the state information of this client with its own neighbors, which happen to be these 6 APs, 4, 6, 9, 10, 8, and 5. And further, if it moves to AP9, AP9 will share its state with its own neighbors, which is AP6, 7, and 10. So as this client roams across different APs on your deployment, each AP shares information of this client with its own neighbors, which is the APs to which the client is likely to roam to next. Now, the other thing that needs to be thought through is what happens when network changes happen. So take an example that AP9 goes away because, let's say, it lost power. The client by default will try and associate to its next closest AP, which happens to be AP6, for example. And when it does that, like earlier, AP6 will send that information, the state information of this client, with AP4 and AP7. And the other thing that will happen is that because AP9's beacons are no longer visible, the APs which considered AP9 as its neighbor earlier, which are AP6, 7, and 10, will remove AP9 from their own neighbor table. Also, what could happen is that a new AP could show up. So for example, let's say AP11 joins the network. Now when AP11 joins the network and AP1, 4, and 6 are its neighbors, obviously the first thing that will happen is that because of AP11's beacons, they will get added to the neighbor table of AP1, AP4, and AP6. And once this happens, AP1, 4, and 6 will send the state information of all the clients that are connected to them, to AP11. That way now AP11 is ready to receive roaming from any of these APs to itself, and it's a part of the control plane. So this is how the distributed control plane in CloudVision Wi-Fi works. So let's see what are the benefits of having such a distributed control plane. The first benefit is that it's robust. There is no single point of failure. no control information went to the management plane. Management plane is not in the path of any control decisions. So if that fails, if the APs lose connectivity to the management plane, the system continues to function. Similarly, if a few APs fail, the distributed plane redistributes itself, as we saw, and hence there is no loss of functionality in the system. So there is no single point of failure in this distributed control plane. The other benefit is that it is scalable. The state information that each AP needs to hold scales linearly with number of clients that connect to an AP, average number of clients that connect to an AP. Because APs only hold information about clients that are likely to roam to it. It doesn't have to manage the list of all the clients across all APs. So if APs are too far away and clients are not likely to jump roam from one AP to the other, there is no point in holding information of those clients across these APs. And as you saw, the state information or the control plane actually propagates as clients move, and hence it's very scalable. And the deployment scaling is also scalable. It's almost indefinitely scalable because, again, as you saw, management plane is not involved. There is no dependence on how big your network is because APs are talking to each other to define the control plane. And the data that is transferred between the AP is transferred locally, so it's fast, it's efficient. It is AES 128-bit encrypted, and as you notice, it does not require a backhaul bandwidth towards the cloud because no information is sent to either the cloud or to the on-premise controller that you might have. So there is no backhaul requirement. So that's the reason it's fast and efficient. It's robust. It's scalable. And this is the introduction to the distributed control plane of CloudVision WiFi. Thank you.